Okay, this is Graphing Lesson 6. We're going to just have a brief introduction to functions and the function notation. And so that you can work with the notation, sort of understand what the definition of a function is, and then domain and range from the function. So a function, so this is sort of the official definition. Once we start working with them, I think you'll get a better sense of it. But for each element in the domain from the first set, gets exactly one element in the second set, which is called the range. So look at this first one on the left. So on the left here, notice that each element in the domain gets exactly one element in the range. It may be easier to look at the one that's not a function. So when would this not be a function? When one element in the domain goes to two elements in the range. That violates the definition of a function. And we'll look more of these in a little bit. But for now, the official definition of a function, for each element in the domain, we get exactly one element in the range. So function notation, really it's the same as we've had before. We have y equals 2x minus 1. We're simply replacing the y and the f of x. Sometimes books will say y equals f of x. Why do we do that? A couple reasons. It's a nice labeling mechanism, right? So if I'm talking about revenue, cost, and profit, I can have r of x, p of x, c of x for revenue, profit, and cost. So it's a nice labeling mechanism. It's also, as I mentioned before, math folks love things really compactly. So in this first one, if I wanted to say find y when x equals 2, that's kind of what I have to write out. But in the same way, I can ask the same question here. I can just say find f of 2. So when I say find f of 2, that means this. I know you don't get it yet, but you will when you just see some examples here. So just examples of what some functions look like. So police estimate the speed at which a car was traveling by measuring its skid marks. So the function, this is read r of L is 2 on the square root of 5L. Can be used where L is the length of a skid mark in feet, and R is the speed. I left out the R. So again, this also sort of re-emphasizes the functional nature of this, that I know the rate at which the car is going if I know the skid mark. So the rate is a function of the skid mark. Okay, so it just makes it a tighter relationship there. So the number of U.S. farms, F in millions, can be approximated by the equation or the function. So we can say equation or function. F of t equals negative 1/50th t plus 2.5, where t is the number of years after 1975. So again, so if I know the number of years after 1975, let's say 1995, that would mean t would be 20 in 1995, and I can tell you about how many farms in millions we had in the U.S. Another one, so the total revenue is the total amount taken in. So a firm determines that when it sells X stereos, its total revenue is given by this formula here. So it's kind of like a formula, right? So r of x equals 280x minus 0.4x squared, where x is the number of stereos. So if I said find r of 7, that would give me the total revenue taken in if I've sold 7 stereos. And I just plug a 7 in. So if I wanted to find r of 7, I would say 280 times 7 minus 0.4 times 7 squared. And whatever that came out to be would be my answer. So the area of a square is a function of the length of one of its sides, right? So if I know one of the sides of a square, I can know the area. So there's a side, you give me that side, I'll know the area. So A of, let's say a side was 4 inches. So A of 4 would be 4 squared, or 16 inches squared if I'm talking about inches. So let's look at the first example here. So the formula for the area of a circle is pi r squared. So here the area is a function of the radius. But we want to write this in function notation. So that's part A. So function notation, what would this be? So it would be a of r equals pi r squared. That's it. I've just used function notation. This is read the a of r, or area, as a function of its radius. What about B? So in part B, determine the area when the radius is 10 yards. So we want to find a of 10. So what's a of 10 going to be? Pi times 10 squared, or 100 pi. Would be the exact value. You can crunch that out. This is yards, so this would be yards squared. You can crunch that on the calculator if you want, get an approximation. We'll just leave it like that. Okay, so given the function f of x equals 2x minus 1, find these particular values here. Find f of 0, f of 3, f of k, f of h plus k. So the first couple aren't bad, right? So f of 0, again, whatever is in here, we put into this spot right here. So f of x equals 2x minus 1, so f of 0 is going to be 2 times 0 minus 1. And then just evaluate it if you can. So 2 times 0 is 0, minus 1 is a negative 1. So f of 0 is negative 1. What about f of 3? So f of 3 is 2 times 3 minus 1. And again, simplify these if you can. So 2 times 3 is 6, minus 1 is 5. What about f of k? A lot of students pause on this one, but we don't change our rule. Whatever's in this little box here goes in to my x box. So it would be 2 times k minus 1. And that's it. We can't simplify that one. We can't combine these. These aren't like terms. What about f of h plus k? Again, we don't change our rule. You got to be a little careful with parentheses here. So 2h plus k minus 1. Is that written right? No. Not a chance, right? It's 2 times the entire quantity in here. So to do that, I've got to put parentheses here. And we'll just leave it like that. If you want to, you can distribute through, but we don't need to here. Okay, domain and range. So domain is the input. Sometimes just the x values. The range, the output, all the y values. So graphically, the domain and range of this is going to be what? So what are the set of all the x values? So that's my domain. Everything from -3 all the way up to 4 is the domain. What about the range? You look at the smallest y value and go up to the biggest y value. Smallest one is down here at 0, and it goes all the way up to 5. So the range is from 0 to 5. Again, the domain, if you wanted to, you can draw a box around it, right? If I drew a box around it, my rectangle, the domain is sort of the width of the rectangle, and the range is the height of the rectangle. Is another way to think about it. Now this is if it's a continuous function in there. So try this one. So draw a box around it so you can find the domain and the range. Okay, so my little box. Best I can. So again, the domain is the width. The range is this part right here, the height. So it's the domain first. I'll just put D. So the domain is everywhere from what? From -1 all the way up to 3. And the range is everything in between, what do we have, -3 all the way up to 5. Okay, find the domain and range of this one. Pause the video here, see if you can do this one. Okay, I may have tricked you. So if you said the domain was everything from -1 to 3, that's not right. Because these aren't connected, right? The only points in my domain are just these x-coordinates. So just -1. We'll put little set braces around here. So -1, 0, 1, 2, 3. Those are all the values in the domain. Now I could not have listed those in the previous problem because there were an infinite number of points, and so I had to use that interval notation. Okay, how about the range? So I usually just go from the smallest to largest. You don't have to, but it's usually best. So the smallest one we pick up at 2, and 3, and 4. So when we have points, a graph of points, we list them. If we have a nice continuous graph, like we did over here, we have to use interval notation. Now what if we're given a function? We could graph these, but sometimes that can get a little tricky. Let's just think about it. Let's do part A. So remember, domain is what can I plug in for x? And it's sometimes easier to think, well, what can't I plug in? What do I need to be careful about? And there are a lot of things, but in here we're going to worry about two things. In particular, in this lesson here, we're going to worry about one thing. We cannot divide by a 0. Can't divide by 0. So my domain can be everything except for the set of numbers that gives me division by 0. And I need to worry about division by 0 in this first one because I've got an x. I don't have to in the second one because I don't have an x in the bottom. But here, if you look at it, what number when I plug it in would give me a 0 in the denominator? Good, a 2. Now, if that's too hard to think about, you can always just say, okay, I'm going to set this equal to 0 and solve. At 2, I get x equals 2. 2 makes that 0. So my domain is everything, all x, such that x cannot be 2. What? What did I just do? Okay, so again, this is that set notation. All x. So the line here means such that. And we know this means x can't be 2. Why can't it be 2? What happens if I plug a 2 in? 3 over 2 minus 2, 2 minus 2 is 0. So 3 over 0 is undefined. But I can plug every other value in. It's not going to make it undefined. I'll have some value. Now if you want to, for me, if you're in Dr. McDaniel's class, you can just write that out in plain old English. All x except x can't be 2. I'm okay with that. But just know, at least be able to pick this out of a lineup if it's in a MyMathLab or something. Okay, how about B? Do I need to worry about anything on B? And in this case, I only give you one thing to worry about. I can't divide by 0. There are some other things, like another one we may see in here is I can't have negatives underneath the square root or any sort of even indexed root. Square root, fourth root, sixth root. But I don't have that here, right? So my domain can be all real numbers. Okay, so it's given the function f of x equals 4 over x minus 2. Find the following. Find f of 1, f of 2, f of 3, then find the domain. Pause the video here. You have enough information to go on to get this one right. All right, welcome back. Did I give enough time to pause it? I hope so. Here we go. F of 1, where am I going to put that 1? Good. You're going to pop it right in for x. So 4 over 1 minus 2, 4 over negative 1, which is negative 4. F of 2, 4 over 2 minus 2, 4 over 0. Uh-oh, this is undefined. So right off the bat, I know that 2 is not in the domain, because the domain are all the possible x values I can plug in, and 2 does not give me something that's defined. Again, domain, the values that I plug in for x that give me a value. 4, negative 4, 3, 1/2, 0.2. But if I can find values that don't work, those are not in my domain. F of 3, 4 over 3 minus 2, 4 over 1, positive 4. The domain, I've already kind of given us a heads up, right? So my domain is everything except for 2. So all x such that x can't be 2. See if you can do this one. Okay, and you can use a table feature on the calculator. We'll look at that in class. But f of 0, when I plug in a 0 here, the square root of 0 minus 2 is the square root of negative 2. This is undefined for real numbers. So no real numbers, no real solutions here. How about f of 1? 1 minus 2. Square root of negative 1. That's not going to work either. That's also undefined. F of 2. 2 minus 2 is the square root of 0. That's just 0. I'm in positive territory now. How about f of 3? Square root of 3 minus 2. Square root of 1, which is 1. F of 4, 4 minus 2. Hopefully you're getting the hang of the function notation. It does take a little practice. Equals, and we can approximate that. at about 1.4 if you want to. So what's my domain here? If we think about it, my domain starts at 2. If you graph this on the calculator, you get something like this. It's kind of like half a parabola turned on its side. So my domain actually starts at 2 and goes all the way to infinity. You could just say x has to be greater than or equal to 2. If you wanted to use set builder notation, I'm okay with either one. So interval notation or set builder notation. And again, that kind of makes sense for how we evaluated these, right? I got to make sure I don't have any negative numbers in here underneath the radical. And a way to do that is you can just take that value that's underneath the radical. We know this has to be greater than or equal to 0. And solve. Easy enough. X is greater than or equal to 2. That's my domain. And then we just kind of dressed it up with set builder notation and interval notation. Vertical line test. Okay, so if I've given you a graph, we want to know is if something is a function. How do we know if it's a function? One thing we can do is we can use a vertical line test. So if every vertical line intersects it and at most one point, it's a function. So for instance, you can mentally or actually physically draw vertical lines. And if it does not intersect it at more than one point, it's a function. So this first one is a function. Yes. What about the second one on the right? The parabola opening up to the right? No, because I cross more than one point almost everywhere, right? Everywhere except for the vertex right here. So this one is not a function.